let us start this lecture with a thought process. Great Swami Vivekananda, who says that they alone live who live for others, and rest are more dead than alive. It's a very profound statement, and most of us are only living for ourselves, and we will get more happiness and satisfaction when we live for others. Now let us recall what we learned in the last lecture. In the last lecture, we looked at the flow pitches in a conversion diversion nozzle, which is comprises of the over expansion of the nozzle, under expansion of the nozzle, and fully expansion of the nozzle. And later on we also discuss what will happen when this expansion wave or the shock waves will be impinging into the free boundary, and how it will be reflecting. If you remember that this either the shock wave or the expansion wave undergoes a unlike reflection from the free boundary, and that we will be looking at now. And today we will be discussing about the various features at the downstream of the nozzle under when it is over expanded and when it is under expanded. So, let us consider now the basically effect of ambient pressure or the back pressure on this nozzle, and let us see that what happens when the conversion nozzle is under expanded. So, let us look at what is happening. This is a conversion diversion nozzle, and when the flow, these are the streamline, I have drawn something, and it is under expanded. That means the pressure at the exit, if you look at this is your exit, PE is greater than the PV back pressure. It will be further expanding at the downstream of the nozzle exit, and so that these are the expansion waves which are being formed emanated from the nozzle exit or the wall. And you can look at these are your free boundary or the jet boundary. And you can see this jet boundary, the shape is changing, and when it is impingence on that, this also shape is changing. It is going basically away, as I told, and then when it is coming over here, if you look at, is reflected as a compression wave, and these compression waves is coalesces and form a shock, an oblique shock, and of course then, but however in the center line, this is your center line of the nozzle, the streamline remains constant. So, therefore, there will be a normal shock and all is joined together, and this is known as shock triple point. And from here, because this will be acting like a solid surface, and then so that oblique shock will be reflected back, and then this oblique shock again will be interacting with this boundary. And keep in mind that this is basically the Mach disk, because the change across this pressure will be much higher as compared to the oblique shock, and so also the losses. And when this oblique shock is impinged into the jet boundary, then it will be, there will be a change in the shape of this jet boundary, and it is also reflected as expansion waves. So, these are basically expansion waves. And again these expansion waves will be reflected from the jet boundary. This is your jet boundary, as these are basically compression waves, and again coalesces into the shock, and again this process of again further this Mach disk is formed, and again oblique shock will be reflected back, and this shock cell will be just goes on repeating till its strength is reduced further. And these features is basically will be going on, and each rocket nozzle will be experiencing, particularly at the higher altitude at beyond which at which the nozzle is designed. And this is also incurs certain pressure losses, and which has to be considered while designing this thing and must be avoided. But however, in case of under expanded nozzle, the losses will be much lower as compared to the over expanded nozzle. Therefore, one always prefer under expanded nozzle over the over expanded nozzle. Now, let us see what happens when the CD nozzle is over expanded. And in this case, at the sock waves are emanated from the nozzle lips, exit lips. So, this is your exit, and then again, as I told earlier, that the center line will be, there will not be any change in the streamline. So, there will be a MAC disc is formed, and this is your normal sock, and we call it as a MAC disc because it will be very thick one. And then this will be this oblique sock will be again reflected by the oblique sock, and this oblique sock impinges into the jet boundary, and then the expansion waves will be formed. These are the basically expansion waves are from on the both the sides, and then these expansion waves again when impinge into this jet boundary, this is your jet boundary, then the compression waves are formed here. These are all compression waves, and these compression waves are coalesces to form a sock wave. And again the MAC disc is formed, and this is again repeated further till its really strength is being reduced. And as I told earlier, when the jet is over expanded, it incurs a lot of losses. As a result, the thrust produced by the rocket nozzle will be lower as compared to the under expanded nozzle, and both the over expanded and under expanded CD nozzle will be having lower thrust as compared to the fully expanded nozzle. So, one has to design in such a way that the over expanded portion of the operation during its flight must be reduced, rather one will go for little or more over expansion such that the losses will be minimized, and that is the things what being done. Now, let us look at what happens, because all this discussion what we have done is considering that there is no boundary layer. However, there will be a boundary layer, and keep in mind that this boundary layer will be there. It may be very thin one, right, because the flow is accelerating, and this is your boundary layer. And when the sock is interacting with this boundary layer, as you know, the pressure will be higher at the downstream of the sock. So, then there will be adverse pressure gradient, and the boundary layer is more likely to be separated out, such that the flow will be, recirculation will be there. And of course, in this condition the pressure will be such that it may have a higher thrust. However, this may be asymmetric in nature, this boundary layer separation, so that it will give you side thrusters. So, this flow separation will be dependent on several parameters, or what are those things, let us look at it. So, flow separation will be depends on basically the angle of divergences, and also the wall pressure, and it will be dependent on the local Mach number what will be there, and local pressure gradient, and wall roughness also plays an important role for initiation of this boundary layer separations, particularly because wall roughness will be turbulence level. If turbulence level is higher, then naturally the flow is less likely to separate, and it will be bearing the higher pressure gradient or adverse pressure gradient. So, for that, of course, while designing, certain thumb rule is being used, which is known as the Sommerfeld criterion for flow separation. That means P E by P A generally will be less than equal to 0.4 to avoid the flow separation, when the P T E, that is by P A, and P T E is equal to basically P T 2, you can say, at the reservoir greater than 16. For alpha, this is your nozzle angle, alpha is less than equal to 30 degree. This angle, that if you look at this angle, is basically, you can say, this is alpha, and less than equal to 30 degree, this is your alpha. And but this is a little thumb rule, and it is also dependent on the Mach number of the flow, local Mach number. So, therefore, the people have conducted experiment and arrived at semi empirical criterion for flow separation, that is being used, that is P E by P A is equal to 1.88 ME minus 1 power to minus 0.64. That means basically it is 1 over that, and P E, that means if Mach number is greater than 1, so naturally this will be a positive, so that pressure, exit pressure will be less than that of the P A, and this criteria is more robust as compared to the Sommerfeld criteria, but Sommerfeld criterion is used as a thumb rule for preliminary design of the rocket nozzle, because you may not be knowing the exit Mach number as such, so that you can really start with this, maybe you can cross check whether it is doing well or not. So, let us now look at the thrust coefficient, what we had discussed or defined earlier. So, we know the thrust coefficient is basically Cf is equal to the ratio of thrust divided by chamber pressure, that is Pc, and At is your throat area, and this At is corresponding to basically choked condition, and that we generally take. So, let us recall the thrust equation for a rocket engine that we had derived earlier, that is the thrust F is equal to m dot P V E plus P E minus P A into the exit area of the nozzle. So, if you look at this is basically momentum thrust, and this portion is your pressure thrust, that already we have discussed, and keep in mind that there is no inlet drag in this, or the ram effect is not there, because this is a non-air breathing engines. And keep in mind that in the rocket engine, except starting and also the shutting down of the rocket engines, the nozzle is choked for most of the time. The expression for the choked mass flow can be derived and as being written as that m dot P is equal to P T 2, that is your the chamber pressure, A star, this is your throat area at choked condition, Keep in mind that under this condition the throat will attain the Mach number 1 or the sonic velocity, and this is aerodynamical choked, and into the root over gamma divided by root over R T T 2. T T 2 is your chamber temperature, R is your specific gas constant, into the 2 by gamma plus 1 power to the gamma plus 1 divided by 2 gamma minus 1. This you can derive very easily, and already we have discussed about the isentropic flow through a variable duct. So, you can get very easily this expression, and we have already derived the exit velocity expression in terms of the temperature, that is 2 gamma RU, RU is your universal gas constant, the TT2 that is your chamber temperature divided by gamma minus 1, m bar is basically molecular weight of the gas, and into 1 minus P by PT2 power to the gamma minus 1 divided by gamma. This already we have derived this expression. what we will be doing, we will be basically using this equation 11 and equation 13 in the expression of equation 1, and then we will get basically expression for the thrust, and you can see that it is having a very big expression, and we can simplify a little bit and recognize that this is basically Ru, universal gas constant by the molecular weight, and this you can basically cancel it out. This portion will be cancel it out, this portion, right, and you can take this term into this root over, and I can write down that F is equal to PT2 by A star, and root over of that I can write down this as a gamma 2 by gamma plus 1, gamma plus 1, gamma minus 1, and this will be 2 gamma. I can say this is basically, I can, instead of writing here, I can write down this will be 2 gamma square gamma minus 1 and into 1 minus Pe by Pt2 gamma minus 1 gamma and plus Pe by Pa, and this is the expression you can get over here. And if you look at, we are going to basically find out an expression for thrust coefficient Cf. Therefore, what we will do, we will have to divide this Cf becomes basically F divided by PCAT, and PT2, keep in mind that PT2 is equal to the PC. So, by doing that, PT2 is equal to the PC, the chamber pressure, and by doing that we can simplifying this expression, already we have written over here previously. So, if I will divide this as PT2 by S star here, PT2 by S star, cancel it, this is nothing but your Cf. So, and when we are doing that, we will have to also do this here, that is PT2 S star. So, that becomes Cf, which is F divided by P2 S star, and this expression already you know, this is same as that, and this became Pe by divided by PT2 minus Pa by PT2 and Ae by A star, and this is also known as epsilon. We will be using expansion ratio Ae by A star. Ae is your exit area of the nozzle, CD nozzle, and A star is your throat area. And you can see from here that Cf is basically function of gamma, and it is function of the pressure ratio, that is Pe by Pt2, and it is also the function of Pa by Pt2, and it is also the function of Ae by A star, that we will see. From this expression indicates basically amplification of the thrust due to expansion in a CD nozzle as compared to the thrust if PT2 acts on the throat area alone. For example, if I consider this is a CD nozzle, and this is the pressure which will be joined into, let us say, chamber pressure PT2, and this is your throat area A star under the choked conditions. You can look at this is the velocity which will be coming over here, and such that P2 is acting on this area A star, and that will be giving a thrust. Due to this divergent portion, divergent duct, the thrust will be increasing, and that gives the amplification how far it will go really beyond this if the pressure PT2 could have acted over the this throat area or the choked area. So, that indicates basically this is the indicator of amplification of thrust. So, as I told earlier, the Cf is a function of Pe by Pt2, the pressure ratio across the nozzle, and also it depends on the atmospheric pressure with respect to the chamber pressure or the, and Ae by A star, this is your expansion ratio, and gamma. And Cf value varies from 0.8 to 1.9, even sometimes you may get much a little bit higher and under ideal condition, but real situation you will get here. In practice, actual Cf is around something 0.98 times of ideal Cf. Keep in mind that Cf from this expression, if you get, I can get the really the ideal one, because this expression, what if you look at this portion is basically we have derived considering the isentropic flow. And whereas if I can measure the thrust, which is much easier to measure under static conditions, and also the we can measure easily the chamber pressure, and under choked condition the throat area is same as that of the choked area. So, if I measure, then I can get the estimate the thrust coefficient experimentally, and this is the ideal one. So, if you look at the actual one will be from the measurement, and this is actual Cf is around 0.98 of the ideal Cf, that means basically 2% error will be there if you just take some theoretical value, right. So, it is really not much, but however always you will have to rely on the experiment to see what is happening. So, with this I will stop over. In the next lecture we will be discussing this thrust coefficient further. Thank you very much for listening to this talk.